In this video, I'd like to continue talking about graphing sinusoidal functions when we are given their equation. And the general approach for this is to first recognize what the parent function for the sine or the cosine looks like. And we can see down below we have the cosine function, since notice that when x is equal to 0, it goes through its maximum point. Whereas if this was the sine function parent function, then at x equals 0, the sine actually goes through a y value of 0. And sine is essentially just shifted pi over 2 radians to the right. They are very similar curves, but just shifted versions of each other. So if this was sine, then we would need to know the parent function for the sine function. But since this is cosine, below we have graphed y is equal to the cosine of x. And from there, we can apply these transformations to determine what the graph actually looks like. And the second piece of information we need is the general sinusoidal equation and what each of the different parameters actually do to the equation. So let me quickly paste that in. And remember for this equation that it could be a multiplied by the sine or the cosine. It doesn't matter, since, again, sine and cosine are just shifted versions of each other. We have a multiplied by the sinusoidal function, and on the inside, on the input, we have b times x plus c, and then plus d on the outside, where a, this coefficient in front, affects the amplitude of the function. If it's negative, it will cause a reflection, but the amplitude won't actually be changed. B, this number multiplied by x, will affect the period. C will create a horizontal shift, and D will affect the midline. It will essentially shift the midline either up or down, depending if D is positive or negative. It will cause a vertical shift. And we essentially just need to look at our given equation and then figure out what A, B, C, and D are actually equal to. So let's find those values. We can see that A is -2, meaning that the amplitude in this case would be the absolute value of -2, which is +2. Then we can look at B, which is the number multiplied by x, and in this case is 1/6, meaning that our period is twice pi over 1/6, or the absolute value of 1/6, which is still 1/6. And we're dividing by a fraction, so that's the same as multiplying by that fraction flipped over, and we get a period of 12 pi. And then we look at our horizontal shift, and since we're not adding to our input, that is 0. And lastly, we have our vertical shift, d, which is -5, which tells us that the midline, or the new equation for our midline, is simply y is equal to -5. So all of these y values will be shifted down 5 units. And from this information, we can actually construct the graph here. Now, if we solve this problem on the Khan Academy exercise that this came from, then we would have an interactive grapher, and there would be 2 points, and we would essentially just need to put those 2 points in correct positions. But if we graph this by hand, it could be a little bit more challenging, but we can get a better understanding of exactly what's happening. Now, the big issue with graphing this is that the parent function goes through a period of 2 pi, and that's what we have scaled here, but we need a period of 12 pi. So it would actually make sense to just start with a fresh coordinate axis and graph the function from there. But we can look at the period last. We can start by applying the vertical shift and the scaling due to the amplitude. So let's start with this vertical shift. We know that we're subtracting 5 on the outside, which means everything moves down 5 units. Or in other words, the midline will now be at y is equal to -5, and I will just draw in that horizontal line there so that we have a reference point. And we know this is the cosine, so it's going to have a maximum value starting when x is equal to 0, but that's going to be affected by this negative here. This negative in front, remember, will cause a reflection, essentially about that midline. So if we were just looking at the parent function, when we carry out that reflection, it will just bring it to the opposite value across from that midline. And then this 2 will change this amplitude to be an amplitude of 2, putting the point right there. But let's actually consider what happens after we shift this midline. We know that the parent function would have an amplitude of 1 and would be at a maximum when x is equal to 0. But we know that we're reflecting that point about the midline, and then we're scaling it by this factor of 2 for its amplitude. So now its amplitude is 1, but we need the amplitude to be 2, meaning this point right here at 0, -7 would actually be on our graph. So we have 1 point so far. And to find another point, now we need to consider this period, which makes things a little bit difficult. Probably the simplest thing we can do in graphing this by hand is just change this scale. So that now, instead of being pi and 2 pi, we can count 6 pi and 12 pi, so that we can actually fit one full period on this right half of the coordinate plane here. And likewise, this would be at -6 pi and -12 pi. But now we can use this new scaling in our information about the period to plot our other points. Since we know that the period can be defined as the distance between two consecutive maximum or minimum values. And we have a minimum value here. So if we go 12 pi to the right, we will get another minimum. And if we go 12 pi to the left, we will get another minimum. Now, the maximums are right in the middle of the minimums. So if we go 12 pi to get to another minimum point, we would just go half that distance, 6 pi, to get to a maximum, meaning that this x value right here at 6 pi, this would be a maximum value. And we know our amplitude is 2. It has to be 2 above the midline. So that would leave us with this point right here. And we also know that there are 12 pi units between two consecutive maximums. So if we go 12 pi units to the left, we get another maximum here. And if we want, we can even figure out where the function intersects the midline, since it's always between the maximum and minimum points. So this point right here would be a midline intersection point. So this one, and this one here. And at this point, we can actually construct our curve. So let me do that very quickly. And we could, of course, check this using a computer graphing program, since that will give us a more accurate picture. But the computer program will let us know if we did this correctly.